Test. Okay, let's look at a trigonometric identities and equations question. So specifically, we're going to be solving equations and making use of trigonometric identities in order to do that. So this is the sort of first exam question. Take a look at it. Part A is pretty simple as long as you use the appropriate identity. So it's 1 mark for finding the identity and plugging it in, 2 marks for fully showing the rearrangement. Part B, obviously you're going to have to use Part A. You have to use Part A to solve Part B. Think about re-representing the equation as a quadratic, solve the quadratic, and then very carefully use that to then solve for the appropriate angles for either your cos or sine, whatever you end up with. And make sure you use whatever method it is you're comfortable with to get all the possible solutions within the range given. So in this case, you're given a range of 0 to 720 degrees. Your calculator, remember, can only ever give you one solution when you do arc cos or arc sine, inverse cos, inverse sine. Your calculator will only give you one solution. There can always be more. So use whichever method you're used to, cast or drawing the graph, to get the remaining solutions. Okay, so I'll give you a go to do that question yourself first. And when you're ready, you can pause the video now. Okay, so first off, we're just going to do a little bit of rearranging. So hopefully you spotted the identity you're going to have to make use of. The most commonly used trigonometric identity, sine squared plus cos squared equals 1. Or in this case, a rearrangement of this, sine squared equals 1 minus cos squared. Okay. The reason we know we have to do that is because in the original we've got a mixture of sine and cos, and in the final we've got only coses, and all that seems to have happened is that the sine squared has disappeared and we're left with cos squareds. So this equation here is what is going to allow us to convert from one of those to the other. So let's rewrite the initial equation, the top one, using this identity. So we've got 4 times sine squared, which in this case we've said is 1 minus cos squared, plus 9 cos x minus 6 equals 0. So let's multiply that all out. And there's not much cancelling that can go on except for these two constants, 4 and minus 6. So let's cancel those out. Everything else will stay the same. And notice I'm writing it in the order of powers of cos. That is to say, this is cos squared, this is cos, and then this is a constant, to make it mimic what a quadratic looks like when you write it in that form. Then just because I don't like the minus numbers at the front, the leading minus numbers, I'm going to multiply everything by minus 1, which is completely valid because I'm equating it to 0. And of course, 0 times minus 1 is 0. Cool. So we've got this, and yeah, indeed that is what we were seeking to find. So now let's see how that helps us with the second part. Okay, so we've got the original expression here. However, we know that this is exactly equivalent to this expression here. So if we've been asked to solve this equation, that's exactly the same as solving this equation, because the equations are equivalent and they have the same solutions. The only thing I then need to remind myself, or remind ourselves, is that x has to be between 0 and 720 degrees. It can be 0, but it can't be 720. Strictly less than 720. Right, so how are we going to do this? So in order to do this kind of question, we're going to have to take this expression and, I suppose, simplify it in some sense. It looks like a quadratic, right? So what we're going to do is, I mean, there's sort of 2 ways you can do this. You can continue working with cos x, keep cos x in the expression as you manipulate it, or you can go for a substitution. I tend to use a substitution just because I don't like writing cos over and over again. So let's, instead of cos, I'm going to just replace it with a letter other than x, obviously. Oh, let me just point out that I seem to have mixed things here slightly. In fact, let me just go back. Oh dear. Right, so throughout this, sorry, let me just make an aside. Bad habit. I've mixed cos theta and cos x a few times there. So let me just correct that actually. Okay, so all of these should be x's, right? Because the original question was in terms of x's. I somehow went for the worst of both worlds and mixed x's and thetas in the same equation, which is nonsense. This identity is still true, of course. It's an identity. It's always true for any theta or any x. But yeah, okay, so we were shown that that's the equation. It can be written as this. Right, so that's part A done. Apologies. And then in this case, for part B, let's also make sure we're working with only x's. Right, so back to the substitution then. I'm going to say, let's use y. So instead of writing cos x each time, I'm just going to write y. And then let me just make a note on the side. I've used the following substitution. I'm treating y as exactly the same thing as cos x. Great. So we've got this quadratic. Let's factorize that quadratic then. So from what I heard earlier, use whatever method of factorization you like, and you should end up with this. And that tells me that y is equal to either 2 or a quarter. Right. And if y is 2 or a quarter, therefore cos x is equal to 2, or cos x is equal to a quarter. So to just highlight what we've done here, let me remove the working. This statement here that I'm moving around, that is completely equivalent, and I suppose I can write the word equivalent by doing this double arrowed symbol. That is an equivalent statement to the following statement. Okay, by deduction, we've deduced that from this, we end up with this. And conveniently, we can reduce this even more because cos x equals 2 has 0 solutions, because cos ranges between -1 and 1. The output can never be bigger than 1. It can't be 2. So therefore, we can reduce it further and say, right, remove that as a possibility. And now I'm left with this. Okay. So all that left-hand side stuff we've shown is equivalent to this right-hand side. And then you can just use your favorite method for determining solutions to trig equations of this form. Yeah, so when I say this form, cos x equals a number, sin x equals a number, you should be used to being able to solve those. My method, as you may remember, is I tend to just draw the graph. So I'm not really, I didn't grow up using cast or anything like this, so I'm not really that comfortable using it. But it's a useful tool if you can use cast. Personally, I just draw the graph. So from 0 to 720, cos x I know looks like this. So that's 360. And then that's 720. Quite pleased with how that came out. So then that's 720. That's 360 there. Let's just put on a few more. 180. That would be 540. Okay. And we want to know when it's a quarter. So a quarter on the graph as a line horizontally would be around there. Right, that's about a quarter, because I know this is 1 up here. Oops. That's 1, so therefore this is about a quarter. And therefore the numbers I'm interested in are all these crossing points. So how many am I going to get? 4 answers, right? Specifically the x values of those red crossing points. Okay, and then I'll use the calculator and I'll say, okay, what's cos inverse of a quarter? And when I work that out on the calculator, what do I get? Let me be approximate here. Cos inverse of a quarter is about 75.5. There we go. So my calculator gives me that number for free. And then the other three solutions we're going to have to use our usual trickery to get. So this one here, the third x, that's clearly exactly 360 after this one, right? Because it does a full cyclical motion before it comes back to the same level. So if I do 360 plus 75.5, I'll get here 335.5. And for this one, people tend to do this in various ways. What I tend to do is I say, okay, 180 minus 75.5 gives me this distance here that I'm marking out. So what's that? So I just did it in my calculator. This is about 104.5, this gap that I'm rubbing along. And then because it's got a bit of symmetry here on the curve, about 180, I can just take that gap, add it onto 180. So 180 plus 104.5, which is the gap length, the 104.5, gives me 284.5. So that one there is when x equals 284.5. Okay. And similar bit of logic. In fact, we don't need to use it because I know this one here will be 360 plus the 284.5, because again, from here, it's a full cycle to get there. So 284.5 plus the 360, I end up with 644.5. Okay, and then that's the answer to the question. Give your answer to one decimal place. Good, I've done that. So there are 4 possible solutions to the original equation, and they are listed as follows.